Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. Here we have solid state devices with respect to the microwave energy, especially the microwave transistors. So far, after learning the bipolar junction transistors of the homojunction and heterojunction type, we have switched to the field effect transistors. After learning the JFET into it, we have the metal to semiconductor field effect transistor, and for the high frequency operations, we have just now gone through the understanding of the high electron mobility transistors and solved two problems based on to them also. Now we are going to address in this video the metal oxide semiconductor field effect transistors that are very popular because they are offering the advantages of power amplifications over the microwave frequencies along with a wide range of voltage control to have the device operation. So let us see the details of this metal oxide semiconductor field effect transistor. So here we start with our topic metal oxide semiconductor field effect transistor. A distinction with respect to this particular device is that we have four terminals to this particular device. So this is the very important point here. As before, we have gone through the several types of the field effect transistors. They were having the source terminal represented by S only. Next to that, we had the gate terminal that used to control the output current that we have called as the drain current, and D is the representation to the last terminal drain that is taking out the flow of electron from the region of semiconductor material of the device after the completion of operation here. So along with the source terminal, gate terminal, drain terminal, we have the fourth terminal into the metal oxide semiconductor field effect transistor called as MOSFET, that it is nothing but the substrate here. So I give only the suffix B to the S here, mentioning the substrate here. So as we have a switching from the JFET to that of the MOSFET, and next to that of we have HEMT. Now we have MOSFET here. Now when we switch from JFET to MOSFET, we have metals into the role here. So when we have the semiconductor material used, for example the silicon, and the metal material that is used as like the aluminum here. So in between the metal aluminum part and the semiconductor silicon part, when the insulating type of the silicon dioxide SiO2 is used, so the structure aluminum silicon dioxide silicon is nothing but the MOSFET called as metal oxide semiconductor field effect transistor. So the first one metal is representing the aluminum here. The SiO2 is the oxide dioxide for the silicon material here we have, and then silicon the semiconductor material here. So instead of silicon we can also go for the germanium or the gallium arsenide material depending on the application at hand. So this is the simple structure that we shall see into the next schematic diagram. So this is the schematic diagram with respect to the MOSFET. So here we have the cross-sectional view. We start from the bottom portion here, the bottom portion that has been grounded here. So here we are considering the P type of the semiconductor material here. So the basic P type semiconductor material that is growing the diffusion N positive region for the heavy doping at these two particular portions here, representing further the source and the drain terminals, whereas the middle terminal that has the dimensions represented D here for the p-type semiconductor material, between the two heavily doped n positives here we have the gate terminal represented by G here. So this is basically giving us the n channel MOSFET here. So in the similar fashion, with the swapping of the n-type and the p-type material, we can go for the p-channel MOSFET also. Next to that, we can also have the complementary metal semiconductor field effect transistor called as CMOS there. And further, the memory devices and all are there, the family members with respect to the MOS technology we can say here. So now these are the important terminals that we have shown: the source, gate, and this is the drain here. Now with respect to the drain terminal, here we have the metal electrode connected, whereas the very important between the metal and the semiconductor, that it is the oxide material, as we have talked, SiO2 will be available here. Now here the length with respect to the dimension of the gate is represented by capital L, whereas this is nothing but the exact channel, because of which we have named it the N channel MOSFET here. Now if we take into consideration the three-dimensional axis representing the Y here, X here, and the Z here intersecting into the origin, we can have the various dimensions marked onto this schematic here. So with respect to the Z dimension, we have capital Z. The depth we can say here, the corresponding width we can have calculated in the direction of the X here, whereas Y will be giving us height of the channel. Now here the different potentials corresponding to the gate, source, and the drain we can provide here. So very first of all, we have gate to source potential giving negative polarity like this and positive polarity like this here, whereas the drain to source potential represented as VDS is provided negative and positive polarities here. So this is nothing but the G terminal, the gate terminal here. Now along with the cross-sectional view of the n-channel MOSFET here, the symbolic representation can also be done here. So this is the symbol. So this is the gate terminal G, the source terminal S, and the drain terminal D here. So the arrow is pointed from G towards the device that is controlling the device operation, and finally the drain current there. Now with respect to the metal oxide semiconductor field effect transistor, we can either have the N channel or the P channel here. So depending on the channels and the potential that has been provided as seen from the previous schematic here, we have the four types to discuss here. So here this is the first type where we have the P-type material here, and in this one also we take the P-type material under consideration here. So when we have the gate potential simply represented as Vg, that is initially equal to 0, so that it should be of the positive type. The positive type is needed so that we can have the channel and further operation when these are the source, gate, and the drain terminals corresponding to the heavily doped n-type regions here and the p-type semiconductor material here. This is called as enhancement type of the n channel MOSFET here. So the enhancement type of the n channel MOSFET is usually off condition. So I just mentioned normally off condition. Whereas the same substrate if we have taken here, and initially whatever the Vg it was equal to 0, when it is required to make negative, so that into the channel here, so this is the n channel, the initial structure is the same here, this is n positive, this is n positive corresponding to the source and drain, and this is for the gate. There it will be the depletion inside the n channel here. Hence this type of the n channel MOSFET is called as depletion type. So this is the depletion type. Here it is n channel, and this one is normally on condition here. So I just mentioned here, normally on here. On the another hand, if we swap the semiconductor materials, here we take the n-type semiconductor substrate, here also n-type semiconductor substrate. Here we have the heavily doped regions with respect to the p-type semiconductor materials. So these are corresponding to the source and the drain terminals at both the cases here. Whereas the middle terminal is nothing but the gate terminal that has been connected with the help of the metal contact here. So now here initially the gate potential that it was 0, when it is required to make negative, so that the enhancement type of the MOSFET is obtained here. So this will be called as enhancement type of the P channel MOSFET here. So here this is made first of all normally off condition here. Whereas when the Vg that it was initially equal to 0 is required to make positive, so that we can have the depletion here. So this is nothing but the P channel. So this becomes the depletion type P channel MOSFET, and here it is in the normally on condition. So these are the various types of the MOSFETs we can say here. In the next schematic we shall discuss the various symbols that differentiate these four, that means the enhancement and depletion type of N channel and P channel MOSFETs. So the symbolic differentiation, the characteristic differentiation we shall see. So here we have one tabulation. In the tabulation we go for the first type, that is having the N channel enhancement type of the metal oxide semiconductor field effect transistor, which is normally into the off condition here. The corresponding symbol with respect to the terminals source, drain and the gate are provided here. Whereas this is the fourth terminal with respect to the substrate that we have shown here. See here, the source, the substrate and the drain are having the separate connections as per this symbol is concerned here. Whereas when we go for the same N channel but a depletion type, which is into the normally on condition, this is the second one, we have a simple change into the symbol here. So instead of having the three separate connections with respect to this one, we have a single solid line going towards the various terminal source, drain and the substrate here, along with the source to be grounded further. So this is the gate potential represented into the symbol also, versus the gate and the source here, and the output current resultant in terms of the drain current is represented flowing from drain terminal towards the device here. So this is the second case here. Now in the third case, instead of having the N channels, we have the P channel, but now for the enhancement type, which is normally off there. So this is the symbol here. While we switch from N channel enhancement type to P channel enhancement type, the change into the symbol is that the substrate that was pointed toward the device, the arrow has been reversed in this particular case here. So it is going towards downward here. Whereas in the fourth case, we have again the P channel, but into the depletion mode. We have the similar symbol as like that of the N channel depletion, but again here from the substrate point here, we have the reversal of the arrow pointing away from the device here. Now this column, the third one, gives us the output characteristics associated with the four types of the metal oxide field effect transistors here. So the output characteristics are obviously with respect to the drain voltage Vd marked onto the horizontal axis of each of these plots here, whereas onto the vertical axis we have plotted the drain current here. So when we are working into the N channel, either enhancement or the depletion type, so that time we get the positive values for the drain current, whereas on increasing the drain voltage in the negative portion here, we get the negative type of the drain current as shown in this particular diagrams here. So these are the various curvatures with respect to the constant values of the gate voltage here. Now the corresponding transfer characteristics are also shown with respect to the N channel enhancement, N channel depletion, P channel enhancement and P channel depletion mode of operation. So these are at the constant values of the gate voltage Vg here. Now we shall take the IV characteristic into the detail for the N channel type of the MOSFET here. So here in the schematic, we have taken the drain voltage represented by Vd in terms of volts here. Whereas onto the vertical axis, we have the drain voltage Id measured in terms of milliamperes if you can take, and this may be with respect to the length of the channel here represented by L here. So here we have the markings 0, then 2, 4, 6, 8, 10, 12, 14, 16 up to 18 for the drain voltage, whereas we can go for 10 milliamperes, 20, 30, 40 and 50 milliamperes here. So now we get these various values. So these various values are with respect to the difference of the gate voltage Vg with that of the thermal voltage Vth. So here initially we have the difference of Vg minus Vth is equal to 10 volts. Then we get it lowered down. So we have 9 volts, 8 volts, then 7 volts, 6 volts, 5 volts, 4 volts. Next to that, here we have 3 volts. This is for 2 volts and 1 volt. So with lowering the difference of Vg with respect to the Vth, we get the low output corresponding to the drain current here. Now initially when the drain voltage was increasing, the drain current was linearly increasing. After that, we come to a saturation point, after which we have the constant value of the drain current, though the drain voltage is increasing. So here we have a separation of linear region and the saturation region. So the separation from linear region to the saturation region is at the bending points that we have shown here. So these are nothing but the pinch off points we can see here. So this is simply the locus of IDS versus VDS. The suffix S that we have represented to the state of saturation here. So after the drain voltage and the drain current are at the saturation level, we find the constant lines with respect to the changes into the drain voltage. So as just now we have seen the drain current versus the supplied drain voltage and the various constant values of the gate voltage here. Now let us have a generalized expression that expresses the output drain current. So here we express the drain current with the symbolic notation of I suffix d. So it is dependent on to the Z divided by L in multiplication to mu suffix n C suffix I. Here we have it in multiplication to the bracket that has the first term Vg minus twice psi suffix b minus Vd divided by 2. So this parenthesis is completed in multiplication to Vd. So here we have the second term inside the bracket that it is 2 divided by 3 times C suffix I in multiplication to twice of epsilon suffix s into q into Na. Here we have that is having the power 1 by 2 in multiplication to the square bracket that has inside Vd added with twice psi suffix b, which is under square root, minus here we have twice of psi suffix b, which is under square root here. So here we complete the square bracket and finally the curly bracket here. So this is the very important expression to obtain the drain current corresponding to the metal oxide semiconductor field effect transistor. So now here we have the various parameters involved in calculation of ID. Here we express one by one. So the very first one that we have mu suffix n. So mu suffix n is nothing but the electron mobility. As electron is the majority charge carrier in terms of the n-type semiconductor materials, we have given the suffix n to it. Whereas along with mu suffix n, we have C suffix I. So C suffix I is the capacitance that has been calculated by taking epsilon suffix I divided by d. So this is the insulator capacitance. So basically epsilon suffix I, this is the dielectric constant with respect to the insulating material measured in terms of farads per meter. D is the dimension we have shown into the schematic in terms of meters. So this becomes calculated in terms of farad per meter square. So this is the capacitance per unit area, that is C suffix I here into the RHS in the two places for the two terms here. So after this capacitance, where epsilon suffix I is the insulator permittivity or the dielectric constant, you can say, we have the representation of the parameter capital V suffix G, which is nothing but the gate voltage that is responsible for the production of the drain current here. Now we have also the representation of psi suffix B at the places in the RHS here, which is computed as capital E suffix I minus capital E suffix F divided by Q here. So this is the potential difference. This is the potential difference between capital E suffix F representing the Fermi level. The Fermi level and E suffix I, the intrinsic Fermi level. Whereas small q is the electron charge, 1.6 into 10 raised to power minus 19 coulombs there. Now here we have epsilon suffix s to be the dielectric constant or the permittivity of the semiconductor here. Whereas epsilon suffix I, as we have discussed before, is the permittivity of insulator. Now after epsilon suffix s, we have the representation of n suffix a here. So n suffix a represents the concentration. So this time this is for the acceptor concentration. Now, just now we have the equation that has represented the drain current dependent on various of the parameters here. As into the characteristics, we have seen the nature of the drain current to be linearly increasing into the linear region, then constant inside the saturation region. So we modify the generalized equation as above into the linear region and then into the saturation region. So for linear region, we can express the drain current as the approximation we can do as capital Z divided by L. These are the two dimensional parameters that we have represented into the schematic diagram. In multiplication to the recently explained mu suffix n mobility, the capacitance per unit area C suffix I in multiplication to the square bracket that has Vg minus Vth in multiplication to the Vd. So this is the gate voltage, this is the threshold voltage, this is the drain voltage. So minus, here we have 1 by 2 added with the square root in the numerator that has epsilon suffix s q into Na divided by psi suffix b, and this is divided by 4 times c suffix I here, and the parenthesis is completed and it is in multiplication to Vd square here. Here we complete the square bracket. This is the expression for drain current into the linear region that we have seen in the characteristic diagram. We can express this equation also in the form where we have the approximation of ID as Z divided by L mu n C suffix I. In the bracket, here we have Vg minus Vth into Vd. For the case we have Vd, the drain voltage, that is very less than that of the difference of Vg minus Vth. So this gives very simplified form, and here the Vth is expressed as we have twice of psi suffix b that has been added into 2 divided by c suffix I in multiplication to epsilon suffix s into q into Na into psi suffix b. This is all under square root here. So this is all for the linear region. Now we go for the saturation region. For the saturation region, we can represent the drain current not simply into the ID but ID suffix SAT for the representation of saturation level here. So it is computed as small m into Z divided by L into the mobility of electron mu suffix n into capital C suffix I in bracket. Here we have Vg minus Vth squared here. So here the small m that has been in multiplication to the Z is having the value 0.5 here. This is nothing but the low value of the doping factor, we can say, and the representation of the drain voltage here. So at the saturation, Vd set will be approximated to the difference of Vg minus Vth as the assumption to obtain the value of the drain current here. Now, along with the knowledge of drain current, it is very essential to have the performance of the device calculated in terms of the transconductance parameter here. So we first of all go for the linear region to compute the transconductance. The expression is given as the transconductance represented by Gm as the ratio of differential of the drain current ID with respect to the differential of gate voltage Vg, provided that we have Vd is equal to constant value here. So this can be further expressed as Z divided by L into mu n into C suffix I into Vd here. And when we go for the saturation region, so that time the transconductance can be represented by G suffix m SAT representing the saturation. So here it is twice into M into Z divided by L mu n Ci in the bracket Vg minus Vth here. So here the meaning of the M is the same as just now we have shown in the expression of drain current here. Now the extension to this, we can express the channel conductance. The channel conductance can be represented as G suffix D, and it is the expression of differential of ID divided by the differential of VD, provided VG, the gate voltage, is at constant level here. So this is further in terms of Z divided by L into mu suffix n C suffix I in the bracket Vg minus Vth here. Next to the expression of G suffix D that we have, we go for the real type of n channel MOSFET here. And at the practical situation, the ID sat, the saturation level of the drain current, is equal to Z times C suffix I in the bracket Vg minus Vth in multiplication to V suffix S. So V suffix S is the saturation velocity of the charge carrier, that it is electron. So this is nothing but the drift velocity at the saturation level, we can say. So in this practical situation, the transconductance Gm is simply Z into C suffix I into this drift velocity at saturation level Vs here. So V suffix S is equal to capital L, the length we have shown into the schematic diagram, divided by the lifetime of the charge carrier represented by tau here. Whereas the threshold voltage Vth on the other hand is given by the expression phi suffix ms divided by q minus q suffix f divided by c suffix I added with twice of psi suffix b added with twice of divided by c suffix I in multiplication to, here we have epsilon suffix s into q into na into psi suffix b, that is under square root here. So here we have the representation of phi suffix ms as the difference of phi suffix m with phi suffix s. So this is nothing but the work function difference, we can say, and this is in terms of electron volt here. So here we have the two work functions, psi suffix m and the psi suffix s. So the differences of the work functions are with respect to the metal part and that of the semiconductor part in the use of MOSFET here. In the earlier expression, we have q suffix f. So these are with respect to the fixed charges involved into the region here. Now we go for equivalent circuitry. So this is the schematic with respect to the equivalent circuitry of a common source MOSFET here. So I just mentioned. As like for the bipolar junction transistor, we have the configurations as like the common base mode or the common emitter configuration or the common collector. So here we have the common source MOSFET configuration here. Now into the equivalent circuitry, on to the left hand side we have here the gate terminal, very important here, and with respect to the source that has been made common at the bottom here. So this is the source. We have very first measure that it is the potential of gate here. So gate potential Vg or Vgs is across these two terminals here, where onto the input side we have the representation of G suffix in, the input one, whereas the capacitance is represented C suffix in. Next to that, we go on to the latter end where we have the drain terminal represented simply by capital D also. The drain voltage with respect to the source common, we have the representation VD. So as this is the output part, we can represent the capacitance C out and the conductance here G out here. Whereas inside we have the representation of the source G suffix M into V suffix G corresponding to the gate voltage here. Whereas the capacitance we can represent C suffix F into B here. The meanings of the various components involved into the equivalent circuitry of the device we can express one by one. So here we first of all mention G suffix IN. G suffix IN is the input conductance. So this is the input conductance due to the leakage current, we can say. Now we have C suffix IN. C suffix IN is a computation made from the multiplication of Z into L into C suffix I. So I just mentioned input capacitance. Whereas capital C suffix FB, that lastly we have represented in the equivalent circuitry, is called as feedback capacitance. We have G suffix OUT corresponding to the value of G suffix D, that is the output conductance. Here the suffix D is corresponding to the output terminal drain here. Now we have lastly C suffix out computed as the product of C suffix I into C suffix S divided by the addition of the two. So this is the sum of two PN junction capacitance, we can say, in the form of series and the semiconductor here. So these are the various parameters involved into the equivalent circuitry. Now with respect to the equivalent circuit, it will be very helpful in determination of the operating frequency. So the operating frequency at the maximum level can be denoted simply by F max or only F suffix M here. So it is simply omega suffix M divided by 2 pi, or it can be expressed as G suffix M, the transconductance we can say, divided by 2 pi into C suffix IN here, or we can also express it as mu suffix N into Vd divided by 2 pi L square here. So the computation of the operating frequency will be dependent on to the electron mobility, the drain voltage, and the length of the gate terminal corresponding to the channel here. Whereas in the saturation region, if we take the situation that V suffix G, the gate voltage, is very greater than the threshold voltage VTH, the transconductance is reduced to the form, here we give Gm suffix SAT for the saturation case, computed as Z divided by L in multiplication to mu N into C suffix I into Vg, or simply Z into C suffix I into V suffix S, the drift velocity corresponding to the saturation state for the charge carrier here. So here we conclude our topic, metal oxide semiconductor field effect transistors, and in the subsequent two lectures we shall be having a practice of simple two problems based on this device operation here. So I hope you enjoy learning the microwave engineering. So here we were dealing with respect to the microwave energy handlers onto the semiconductor platform, and these were in the form of field effect transistors. So for more information and the knowledge of the subject, you can subscribe to Ekeeda channel. Thank you.